Hey everyone, thanks for joining. My name is Eric, and in this video I'm going to show you how to use Python to generate these cool watercolor images. Before we jump into the code, I want to give you a high-level overview of how this process works. We basically start off with a base image, and in our case this is going to be an octagon. We make it highly transparent, and then we layer it on top of itself dozens, or if you wanted to, even hundreds of times. The caveat is that on each layer we're deforming the edge by splitting each side into smaller sections and moving the midpoints. When we do that and we combine them across all these iterations that we define, you start to get this watercolor effect where the center is thicker, a little more well defined, and the edge becomes foggier. There's a lot of really cool things you can do with this, and this project was actually based on an article written by Tyler Hobbs. I'll put a link in the description so you can see kind of his process and where this idea came from. The last thing I want to show you before we finally start programming is another result of the same system, just without any deformation. I want you to keep this image in mind as we build out the program so that you can understand what we're coming from as we create these watercolor images. Having said all that, let's finally start working through the program itself. The main library that we will be using is something called PyCairo, which allows us to draw vector images in Python. There is no octagon vector image, at least that I'm aware of, so we're actually going to build out a function ourselves that will draw it for us using some primitive shapes, which is pretty exciting. So we'll start off with these import statements. So we're going to import Cairo, system, argparse, copy, math, random, and I think that that's all we need. Actually, I'm going to increase the size of this so that people can see. I hope that works. I hope that's helpful. I think those are all the imports we need. Cairo is referring to that Cairo library that I mentioned. Again, just to reiterate, I'll put the link to that in the description. So I think the last time I did one of these Python videos, I bounced around the program a lot. I think this time I'm actually just going to work from the top down. So the first thing we're going to define is a float generator for float values or decimal values. And it's going to be a Python lambda function. So we can actually say float gen equals lambda a comma b colon random dot uniform a underscore b. Or not underscore, a comma b. Basically, we're just going to use this to create our colors. So we're going to define a empty array of colors. We're going to do a loop. You can play around with the values on this. I put in 15 colors, it looks like. And it's difficult to choose what the colors could be. I started with just going crazy and complete randomness, no restraints whatsoever. But it doesn't look very good when you're making watercolor that's pure white or pure black. It just doesn't, I don't know, it doesn't work very well. So I put some restrictions on here. Again, you can see what you like, play around with these values. And we can also parameterize these where we pass them in when we run the program. But I'll leave that up to you. So what I did was 0.4 and 0.75. So we're going to pick an RGB value between those. We're going to add 3 of these for the RGB. So float gen 0.4, 0.75, and then one more, 0.75. I think that's right. So we've just put those in our color array. We'll pull from those later. So now I'm going to work through the first function, which is our octagon function. We're literally just drawing an octagon. What it's going to receive is the X and Y coordinate for the center of the octagon, and then it's going to get its side length. There's going to be 8 sides. They're all going to have the same length. So X, origin, Y, origin, and side. We're just going to pull these down, X, Y. And then for side, we're not going to set it directly to a variable. We're going to set the diameter to side divided by math dot square root. Now, I got to be honest, it's been a while since I worked on these functions. So it's slightly possible that that's referring to, I'm trying to think about this. I don't know. So I believe that we're making perfect octagons, but I guess we'll have to dispel some belief here because it's probably been close to a year since I actually worked on this. So we're going to define another empty array, and we're going to append our points for the octagon, and then we'll draw it with PyCairo later in the main function. We're basically just using this function, this octagon function, to return a shape object, but that shape object is literally just an array of points or vertices for the octagon. So octagon is an empty thing. We're going to say x plus equals side. Oh, I'm sorry. Actually, we need to append the current x and y. Oh, okay. I see. I've already made a mistake. So the x origin and the y origin, I don't think that is the center. That's actually the origin point. So we're actually going to append that to begin with. Append x and y. And it's important that you put these other parentheses around because we're not, we have to append a tuple value. So we're essentially appending a coordinate and not an individual value. So oct.append x, y, oct. We've added side to x. I think this is essentially the top side of the octagon. So it's just straight. There's no y value change like there will be for the corners essentially. So oct.append x, y. We're going to be doing that a lot, so let's just copy that. And then we're just working our way around the octagon. So it's going to be x plus equals d. So the d, oh, I see. Okay. I think d was diagonal. I don't think d was diameter. I'm making tons of mistakes. I promise this is my code. It's just a matter of forgetting my thought process. So y plus equals d. And then we're going to append those. This isn't the most exciting part. We're basically just working our way all the way around the octagon. So y, we're coming down the right side now, so y plus side. I'm going to append x minus equals d, y plus equals d. And that's the bottom right diagonal of this octagon. X minus equals side, append x minus equal d, y minus equal d, append y minus equal side, append, and I think we're almost there. We've got one more, so x plus equal, this is the top left corner or the top left diagonal, y minus equal d. So that's the octagon. We've appended all the vertices or the points around the octagon, and now we're going to return oct. So this function will just return that array. Fairly straightforward. Now we can move on to the, I guess I'll go ahead and do the deform function now that we've already seen kind of how the octagon works. So this function is going to, so whatever shape we give it, it's going to define midpoints for every side, but it's going to move those midpoints with whatever variance that we've provided. If we do that enough times, we start to get some extremely different shapes from the same base shape. So let's build out this function. We need to give it a shape. We'll give it iterations, which is how many times we want to deform it before it's returned. And then we're going to give it variance, which is just a range that we're going to use to figure out how much it can move the endpoint, or the midpoint, not the endpoint. So for I in range iterations, for j in range, so we're going to do the length of the shape, so of all the points, -1. So we're actually starting at the last value in the shape array. We're working down to 0, so we need to specify that we're incrementing by -1. We're basically going up by -1, so we're really going down. We're going from the back of the array to the front. And the reason I do that It's a little hacky, but it's just because we're inserting a lot of midpoints, and it just felt easier to work from the back to the front. So midpoint equals shape j minus 1. So we're grabbing the value before the last one. So we're just getting the 2 points that are making a side, essentially. So we're grabbing that point, and then we need to get the x value. Then we're going to add it to the x value for the other point that's forming this side. So j, grab the x value from that point. We've added those, and we're dividing by 2. So we found the mid x value for this side. I hope that makes sense. The last thing we're going to do before we move on to the y value is apply our variance. So we're going to use that same float gen function up here that we defined for the colors that we used to create the colors, and we're going to apply it to the variance we provided. So negative variance, variance. So we're picking a variance on that range. Then we're going to do the exact same thing. I'm actually just going to copy this whole thing. So this is for the x value of the midpoint. Now we've got to do the y. The only difference is that for these shape points, we're just going to do the second value in the array, which is it's just a tuple. So we're grabbing the y value. We're applying the variance the same way. This, as long as I did that correctly, that should be the midpoint. And since we're working backwards, we can just do shape.insert j midpoint. We've inserted it. Once we do that through all of the iterations, we can just return shape. I think that is correct. We've edited the shape and we are returning it. It's adding midpoints, but it's also moving the midpoints around. So that's it for the functions that we have to provide. Now we can start with the main. This is definitely one of the most boring parts. This happened in my last generative art tutorial as well, but we're going to include a lot of optional command line arguments that you can pass in using the argparse library. So parser equals argparse.argument parser.add argument width default equals 1000 type equals int. Now this is basically the way that all of these values are going to work. I'm actually just going to copy in everything that I have for these values so that I can talk about them without typing them out. You can definitely copy them down. I'll also have the code in a repo like usual, so don't feel like you have to. But I'd rather explain these without taking the time and distraction of typing them out. So we've got, actually I just copied width twice. So there's width and height. That's pretty self-explanatory. That's going to be the size of the image. The defaults are 1000 by 1500. You can play around with that. But the rest of these values can be a little complicated. So this initial value here, -i or -- initial, the default is 120. This is actually referring to the initial deformation that we're placing on this is actually referring to the initial deformation that we're placing on the shape. What I mean by initial is when we're creating the base shape before we start layering them. It's a little complicated, and it'll make a little bit more sense when we get into the final kind of algorithm. The deviation, it's a lower value, and that's because this is the deviation that's going to be in place for the actual layers themselves. There's going to be less deviation since we've already created this more variable base shape. Again, I think that'll make a lot more sense when you actually see it. So base deforms and final deforms, just like initial and deviation, they're kind of related. The base deforms are how many times we're going to deform the octagon before we start layering it, and the final deforms is how many times we're going to deform it as we're layering it. Min shapes is the minimum of layers we're going to have per octagon, and max shapes is the maximum number of layers we're going to have per octagon. And then the shape alpha is how transparent the octagons will be. The higher the value of the shape alpha, the less foggy your watercolor image will look. It'll be a lot more filled out, and eventually it'll just be kind of a maxed out image of full transparency, so the colors won't bleed into each other. We'll play with that. We'll do a lot of variations once we finally finish. So we need to pull these values down into usable variables. Height initial equals args dot initial, deviation equals args dot deviation. I really like this argparse library just because you can have a lot of optional command line arguments. So it almost makes it feel like a command line tool, even though you're running a simple Python program, which I think is pretty cool. You don't have to provide the defaults. Deforms equals args dot final deforms. Then min shapes equals args dot min shapes. Max shapes equals args dot max shapes. Then the last one is shape alpha equals args dot shape alpha. Okay, so now we're kind of in the end game here. We've got about maybe 10 or 15 lines of code left, I think. We need to use our PyCairo vector drawing library. We have to create an image surface on which to draw, and then create a context object to draw with. So what that looks like, IMS equals Cairo, and you can call that whatever you want. I'm just using IMS because it's an image surface. Cairo.image surface, Cairo.format ARGB 32 width and height. So we've created this image surface on which to draw. We can use RGB values that also have transparency or alpha values as well. So, and then there's CR equals Cairo.context, and for the context we're passing in that image surface that we just created. I'm going to set the source RGB to this wider value. This is probably something else that we could parameterize. I'll leave you to do that. I think that would be really cool. You could have a darker background, lighter background, or just a colorful background, kind of whatever you want. But we're just going to use this 0.9, 0.9, 0.9 to draw the background of the image. So cr.rectangle. This is the first thing that we're drawing. 0, 0, width, height. So that's actually being drawn because we haven't called the octagon. Well, the octagon isn't drawing anything regardless, so this really is the very first thing we've drawn. But we still need to call cr.fill. So we're filling that rectangle that we just drew with the color that we set to source RGB. Now I've got in my notes to set line width to 1. I gotta be honest, I'm not sure if we need that line because I don't think we're drawing an outline for the rectangle. We're not drawing an outline for the octagons, but I'm gonna leave it in just in case. Now this is the final part. This is kind of the algorithm of deforming and drawing the octagons, laying them on top of each other, moving through the image as we create this watercolor. So I'm just gonna work through this. 4p in range, negative int height times 0.2. We're starting 20% above the top of the image. So some octagons are being drawn off screen. That's just to make sure that we don't have any white space or dead space at the top of the image. And we're doing the exact same thing at the bottom. So we're going to height times 1.2. So 120% of the height of the image. And then we're iterating by 60 pixels. So this p value, I don't know why I named it p, it's essentially the rows of octagons that we're drawing. There's not a lot of variability there. We can go ahead and set, well, just for the sake of keeping everything kind of organized, I'll add 4j in range random.randint min shapes, max shapes. So these are going to be, this is going to decide the number of layers that there are going to be for this octagon that's being drawn. So having that in mind, let's actually go back. I probably should have just gone ahead and done this to begin with. We're going to grab a color, then we're going to define a shape size, and then we're going to use our deform function to create the base shape for the layers. So cr.set source RGB A. So it's important to do RGB A because we're not just setting a color, we're also defining a transparency value or an alpha. Random.choice colors. So we've chosen a color. Remember that our colors contain 3 values, so we're going to grab the first one. Random.choice colors 1. Random.choice colors 2. Shape alpha. I think let me make sure that I did everything correctly. I feel like I've missed something. Yes, I missed this parenthesis here. So, and I don't think this is supposed to be here. So we've set these colors. I don't remember exactly why I'm choosing a random color from this array each time and not just choosing a color. And then I think that is probably the better way that it could be. So you could do random choice colors, set it to a color variable, and then use that variable to pull 0, 1, and 2 from it, and then still set that shape alpha at the beginning. But that's another thing that I'll leave to you as an enhancement. So we've chosen the color, we've got that squared away, we've set it as a source RGB, so whatever we draw from now on will be done in that color. Now we need to define our shape. So shape equals octagon. This is the octagon function that we defined near the beginning of the video. We're going to give it, remember that our arguments for the octagon are X origin, Y origin, and side. So octagon random.rand int -100 width plus 100. So we're choosing an X origin somewhere in this row from beyond the left of the image and beyond the right of the image. Basically the same thing we did with the height. We're just making sure that we aren't restricting our octagons to be drawn within the edges of the image. So we've done that. For Y origin, we're just passing in P. Again, I don't really know why I called that P. Random.rand int 100 300. Now this is another thing that I'll point out that could have been passed in as an argument. This is just the size of the shape itself. It's somewhere between 100 and 300. Now that we have the shape, we can create our base shape. So base shape equals deform shape base deforms initial. So remember that our base deforms instead of final deforms. The difference here is that we're going to use this to create our base, and I think that will mean we will deform it less times because we still want it to have a little bit of a solid shape. If you deform it too much, then your final layers are going to vary wildly because they're not working off of a somewhat solid shape. So shape, base deforms, initial. This initial value is going to generally be larger than our final deviation value for kind of the same reason. We want it to be somewhat of a solid shape, but most of the deformation needs to take place here so that the layers actually have something to work off of instead of just an octagon. So it's a balancing act. Basically, the base deforms and initial have to work together, and we'll see a lot of different examples of that once we finish this program, if I'll ever stop talking and actually code. So for j in range random.rand int. Oh, what in the world am I doing? I've already done this. I'm trying to, oh man, I don't even know. So for j in range random.rand int min shapes, max shapes. So this is where we are layering. So we have the base shape. We're going to say temp shape equals copy, and copy was one of our arguments, or copy is one of our imported packages. So copy.deepCopy base shape. We've copied the base shape. We're going to define a layer as another deformation of this base shape. So deform temp shape final deforms deviation. So we're doing the same thing that we did with the base shape, except we're doing more deforms with a lower variance. For I in range, the length of the layer, but we're going to step through each of those points and we're going to draw lines between them. Line 2. We're basically drawing our shape. So layer I 0, layer I 1. Oops. Layer I 1. So that the X value and the Y value of so I is referring to the point in this layer shape, and then we're grabbing the X and Y value of that point. After we draw the line or draw the shape, we're going to do cr.fill just like the background. We're going to fill in this wildly deformed shape, and then we can write ims.write to PNG. We're literally saving the result. Let me finish this up and then we'll make sure we've got everything okay. Name equals main. Oops. Main. Okay. So I hope this makes sense. I realize that that's complicated. I gotta be honest, even if I don't look at this for a while, I stop understanding it pretty quickly. It is somewhat complex. The most important thing to remember are those initial images we looked at. So we're starting off with these octagons, we're drawing them in rows, and then we're going through each octagon and we're grabbing midpoints along each side and we're moving that midpoint somewhere, as some of the shapes may maintain most of their form and some of them may change greatly. So I think we're ready to run it. I'm going to pull in my terminal and we'll just see what we've got. So I've got this watercolor.python file. So we need to run python watercolor.py, and then we can pass in a lot of arguments, but they all have defaults. So just to see if this works, I'm just going to run it like it is. I'm actually extremely surprised that it did. Okay, so yeah, that's a different image than what we had. I'm going to pull in the terminal again and just run it again so you can see. I think we did it. I think that looks great. I'm deeply surprised that worked the first time. We'll just run it a couple more times so we can see. I think it looks pretty good. And this is just with the defaults. So what I want to do now is kind of run through how to use these arguments to start introducing some variability to your results. So we're going to say python watercolor.py. Now let me actually pull back up the code so we can look at what our arguments are. So Python, actually I don't know if you can see this. Let me make this a little bit bigger. Oops. Watercolor.py. Okay, so we've got width and height. Let's make this width and height a little bit bigger just so we can see what it looks like. So we'll say 2000 width, height, we'll say 3000. Width of 2000, height of 3000. Let's do height 1500. Dash I, this is the initial deviation. So we're going to make a basic one. Let's do that. Let's make one without a lot of deformation. So initially, let's just say 1. We're going to do 1 deformation. We're going to do 1. Okay, I'm sorry. That's not the deviation. See, even I'm having a hard time with this. This is why it's important for us to step through it. So this initial deformation is the variance that we're providing. That's why you can look at this default 120. So we're going to set it to 1, which basically means if nothing's happening. We're not going to deform at all. We're going to do the same thing for deviation. And then I actually don't think we have to change anything else because since the variance is so low, the shapes won't really deform. So we're going to run this. I'm going to pull back over here and we're going to look at it. So yeah, so we've changed the size of the image and you can see that we're left with these. The midpoints have theoretically moved by a maximum of maybe somewhere between 1 to 4 pixels because we deformed the image or the octagon 4 times. So if we bump those numbers up, let me pull back up the code. Let's change these numbers back to their defaults, or let's just leave them as their defaults. But let's change the number of deforms. So base deforms, we're going to set it to 3. And then for final deforms, well, FD, we're going to set it, let's just go crazy and do 6. Okay? Let's see what that looks like. It's going to take a little bit longer to run because we're doing the deforming significantly more times. The image or the octagon gets a lot larger, so it takes longer to do. So it's going to take a little bit longer for it to compute. I don't think it's already worked. Okay, here it comes. So now it's being drawn. I don't like that very much. Well, I guess it looks pretty good. There's a lot more color bleed, but we can see the effects of our transparency if we adjust that as well. Let's see. Let's drop this down so it doesn't take quite as long this time. We'll drop it back to the default, but then I'll bump up the shape alpha, and you'll see kind of what it looks like if it's even slightly larger. So we're gonna go from 0.02 to 0.2, and you'll see the effect that that has on our image. The colors are a lot more well defined. You can actually start to see a little bit of the, well, that looks terrible. I don't know why it kept its shape. It's like deforming it even further. What in the world just happened? I don't even know how that works. Let's change this. I don't know why that happened. It's like it squished the image. That's not what it actually looks like. Let's just run this again. Okay, let's close this. Open it back up. Okay, so these deep values, you can see kind of the outlines of our deformation. So if we could zoom in that without messing the entire image up, each one of these points, like these sharp points, is a midpoint that has just been moved out farther than its neighbors. So it's creating that variance. But without the transparency, you're getting these distinct shapes. So let's run the exact same thing, but we'll drop the transparency back down to 0.02. It looks a little bit softer. It looks a little foggier. I think it looks a lot better. Let's do the transparency like that, and let's bump up the initial deforms to, or the initial variance to 300, and the deviation to 100. So that's a pretty big change. Our defaults were 120, and I think it was 50. The colors are going to spread out a little bit more. They're going to cover a little bit more of the field. I think that looks pretty good. Let's do one more with a much lower transparency. So I'm going to drop this down to 0.001. And you can see that it's so transparent, maybe it's too low. Maybe they don't even register at all. I'm not 100% sure on that. They'll start coming up if we bump up the deforms, I think. Actually, they won't. They'll come up if we bump up the max and min shape. So MS, was it MS? Mins. Oh, it was mins. So we're going to bump up the shapes. Mins to 30. I think it's on, oh, it's on 20 now, so let's bump this up to 50. And then maxes to 50. We'll just do 52. Actually, this might be a bad idea because I think it's going to take a while. So since it's going to take so long, let's just put this back the way it was because I want to see what it looks like with a lot more shapes. We're going to let that run. Uh-oh. Empty range for rand range. Well, that's interesting. So I guess we did have a problem. Let's find out what the issue is with this. Is that just because... What happened here? Oh, is it because I put this dash? Yes. So no dash on the actual arguments themselves. Let's just see what it looks like with a lot higher layer count. So it's almost kind of the same thing as when we increase the transparency. You get more filled out shapes, but since it's just different since it's just more layers, you still get the cool edges, but the colors are mixing into these kind of darker splotches. I don't like that as much, so I'm just going to drop that back down to the default. I want to run it one more time just so we can see it. I want to thank you so much for watching this video. I hope it was informative. I hope it was fun. I realize that I kind of rambled a little bit with the code. It's been a long time since I've worked on this project, but it was super fun. I'll put the link in the description to the article that I got the idea for this project from. He kind of lays out the process in a lot better way than I probably explained it. But I hope you learned something. If you did, or if you just enjoyed the video, remember to hit the subscribe button. Leave me a comment letting me know what you think. I did another generative art tutorial before on the solar system setup. If that one along with this is fun, I'd love to keep doing them. I enjoy making the videos. I definitely enjoy working on generative art projects. They're really cool. It's just amazing to be able to see visual output from code, because it's something that we don't get to see very often. It's like something is in the real world. You could print it and put it into a poster frame and it would be there on your wall, and it exists, and we don't get that a lot in the programming world, so it's just really exciting. I'll see you next time, but for now, that's all I got. Thanks for watching.